At Agilent Technologies, we know the challenges chromatographers face today. That's why we develop new products to make their work easier with features that will help to produce faster, reliable, accurate, and cost-effective results in traditional labs or whenever mobility is required. Which is the best carrier gas to achieve those objectives? Around 90% of the existing GC instruments run with helium as carrier gas. Some people still use nitrogen, probably because it was installed this way when they work with packed columns. However, some people have already started to enjoy the benefits of using hydrogen as carrier gas in their GCs. Does the choice of the carrier gas interfere with the chromatography process? Yes, it does, through its diffusivity and viscosity properties. You have certainly seen the so-called Van Dinter curves, plotting plate height against gas velocity, where the optimum gas velocity is at the lowest point of the curve. The larger the plate height, the worse the separation. Do you want to know why hydrogen is the best carrier gas? Hydrogen has the widest flow range, so fast analysis is possible. It is much cheaper than helium, and besides GC, it can also be used with MS systems. By changing to hydrogen, we not only benefit from faster analysis, but we also benefit from a higher response. As the peaks elute faster, the height of the peaks will also be higher. For a similar signal to noise, one can inject half of the sample, from which we can benefit in less contamination of the system. The pressures for using hydrogen are the same as we use with helium. Due to the lower hydrogen viscosity, we can get approximately double linear velocity. That's why hydrogen is the preferred gas, for instance, when using GC-GC MSD with microfluidics technology and dual thermal mass external ovens. Nitrogen is still used in many packed columns applications, as it is very cheap and can also do the required job for an easy application or when helium is not available or hydrogen is not an option. Helium is as good as hydrogen if inlet pressures are below about 50 kilopascals, but requires slower GC at higher inlet pressures when using longer columns, being the difference roughly a factor of 2 when above 150 kilopascals must be applied for helium. Some safety and proper use considerations need to be implemented when switching from helium to hydrogen, and more specifically when AMS detector is in place. Our challenge as analytical chemists is to do this conversion without altering performance criteria. Time should be allotted for adapting the method, optimization, and resolving potential hardware problems. Some areas will need your attention. You should consider to choose the proper column dimensions and the correct analytical conditions. The quality of the gas is key for success. Sourced by a cylinder or a gas generator, make sure you get a good one with a low specs for water and oxygen and assuming a consistent purity over time. You should consider changing the pipe with chromatographic quality stainless steel tubing for cleanliness and safety. Consider the GC-MS required hardware changes according to manufacturer instructions. Choose the right chromatographic conditions. You can obtain the optimized method parameters fast and easily using free applications such as the Agilent Flow Calculator and Method Translator. Besides the intrinsic safety of the GCs, when connecting a hydrogen source of GC, we recommend to install an integrated hydrogen sensor. It will switch automatically to an inert carrier in case of detecting a potential explosive atmosphere in the GC oven. Some hydrogen generators have these safety features already in place, so they stop generating hydrogen if a leak in the GC oven is detected. There are new features also implemented to save gas consumption and electricity in modern GCs, as the Agilent 7890B sleep-wake modes of operation that reduce the gas consumption by changing automatically to a cheaper carrier gas while the GC is in the idle status. There will be some issues when specifically switching GCMS methods to hydrogen. Most of them can be minimized with proper instrument setup and conditioning steps. In summary, the technology is completely ready for the labs to use hydrogen for the analysis in a safe, reliable and cost-effective way.